Well, I think we can start. What do you think? That's
okay.
Yes.
I think it's 1:30 p.m. for you, right? And
It's 1:30, yes. So I'm going to actually
2:30
start
for
sharing
us.
my screen.
Okay. Ananda, you can start the recording.
Estamos
Ananda
ao
pode
vivo.
começar a gravar.
I think it's already going.
Okay. So yes, we're live. Good. So hello everyone. Welcome to today's session. I hope you all are having a good time. At least I am. And for those of you just joining us, please welcome. Now I'm pleased to introduce today's afternoon speaker, Professor John Donoghue from the University of Massachusetts, Amherst, where now he holds a Distinguished Professor Emeritus title. But he has also been a scientific associate at CERN and a visiting researcher at the IHES at Biot in France. Well, Professor Donoghue has a number of honors and awards. Just to mention a few, he has the Chancellor's Medal and Distinguished Faculty Lectureship. He is a fellow in an American Physical Society. And he was also the Erwin Schrödinger Visiting Professor at the University of Vienna. He has also been part in several, let's say, service activities for research, such as a divisional associate editor for the Physical Review Letters, the Scientific Advisory Council for the Particle Data Group, a scientific director of the famous Theoretical Advanced Study Institute. As you all know, the TASI lectures are rather well known for us. The J.J. Noriko Sakurai Dissertation Prize Selection Committee, among others. Well, Professor Donoghue, solo or together with several collaborators, has established a rich, broad, and prolific research production with highly cited papers throughout the years on many topics, ranging from theoretical particle physics to gravity and cosmology. He's famous for a number of papers. I can mention, for instance, two of them. One, he has written with a former PhD student, which certainly known for some of you in the audience, Professor Gustavo Burdman. He's a professor in USP. In this paper, in summary, they show how to consistently unify chiral and heavy quark symmetries. But he has also some famous papers studying general relativity as an effective quantum field theory. Works that together with a more recent one, if I'm not mistaken, from 2004, 2005, that he has written with Professor Barry Hostin, which they show that the classical effects can be obtained from loop diagrams. All those works have been the basis of many current papers using modern amplitude methods to describe and obtain classical observables in general relativity, as well as successful descriptions of black hole binary dynamics. More recently, and that's the part where I came in, he has been involved in the investigation of a quantum field theory of gravity, which is quadratic gravity, an investigation which has rendered some very interesting byproducts, so to speak, which we hope to see today in his talk. So after this very long introduction, I think we're all anxious to hear what he has to say on this latest work. I mean, of course, I already know the content of the talk, but I promise I will not give you any spoilers. So John, we love to hear from you. The audience is all yours now.
Okay, thank you, Gabriel, for that nice introduction. Of course, it's dangerous having your collaborator as your chairman because he's been interested in giving you unlimited time to talk about his own work. Anyway, I have these three topics that I'd like to talk to you about, and I guarantee you that they're actually tied together in some logical way. The arrow of causality, arrow of time, higher derivative theories, and quadratic gravity. Can everyone see my slides okay? Is that okay? The motivation here, as Gabriel mentioned, comes from quadratic gravity which is a renormalizable quantum field theory of gravity, which sounds like it should be the best thing in the world. But there's always a price to pay. And the price here is that because the curvature is their second derivative, the curvature squared terms in quadratic gravity have 4 derivatives. And higher derivative theories have a bunch of things that people think they know about it, some of which are correct and some of which are not. And so we've been exploring the quantum field theory of such theories. And the topics today are actually not quadratic gravity, but they're byproducts of things I learned while going through this. And so I thought you might be interested in them. One of them is a very, very general thing about the arrow of time. We all know that the world progresses as a function of time, and this is often thought to be a mystery. However, all discussions that I know of miss something, that is that quantum field theory actually has an arrow of causality in it. It has an arrow. And I feel a bit embarrassed talking about it because it's really not anything but standard quantum field theory, but it is missed. Moreover, the conclusion is actually quite interesting. It's basically that our arrow of time that we feel in a daily life comes from quantum physics. So I'll try to explain that. The other topic is higher derivative theories, which this Ostrogradsky theorem, which I'll talk about, says that they're all unstable. They're almost never used in particle physics. But the Ostrogradsky theorem actually is not also valid in at least some quantum field theories. So both of these have the effect that quantum physics even implies things in our classical world. So here's the introduction to the arrow of time physics. Basically, it goes back to Eddington, and it basically is that the microscopic laws are time symmetric, and there's nothing in classical physics that gives you a direction of time. And so it becomes, the more you think about it, the more convinced you are that there is some issue with the arrow of time. Here are some quotes that are more modern than Eddington. Ravelli's is lovely. The difference between past and future, cause and effect, memory and hope, regret and intention. In the laws of physics, there is no such difference. And the Carroll and George Ellis quotes are similar, that the foundational dynamics is reversible. And it's easy to say. The fundamental classical physics comes from a principle of least action. It's defined by a Lagrangian. The Lagrangian is symmetric under t goes to minus t. Every solution in one direction has a solution in the other direction. And there's nothing that distinguishes positive time and negative time. Many people feel that invoking the second law solves that, because the second law says that entropy increases with time, so the time is the direction that entropy increases. But if you think about it some more, it doesn't really solve it, because the second law could also work in either direction. In classical physics, you could have a system here where the entropy increases with increasing time, and a system somewhere distant behind the moon is the phrase where the entropy increases with minus t. Those are equally plausible in classical physics. And so you in fact need to explain the arrow of thermodynamics, which then, if you have that, then you have the sense of the arrow of time. Some authors conclude this is just a symmetry breaking effect that due to the Big Bang, why ice cubes melt and don't melt is something was going on 14 billion years ago at the Big Bang. And so is it really true that our daily experience depends on something that happened at the Big Bang? That's in some sense a motivation for this. I have a few things I have to say, just as points of interest. One is, of course, in special relativity, there's no unique time-like direction, but there is a sense of a past light cone and a future light cone, and causal influences come from within the past light cone and influence the future light cone. So causality is in some ways what replaces just the flow of time in a theory with special relativity. Time itself is also a convention. Just like some languages are written left to right, others are written right to left, we could measure time in increasing amounts or measure time in decreasing amounts. There's a convention associated with that, and we could have had clocks here running to increasing amounts and clocks behind the moon running decreasing, but nevertheless, that's not what we're talking about. What we're talking about is that there's a directionality, whether you measure it in increasing or decreasing amounts. There are other conventions that you come across as you're doing this. We sometimes talk about reactions as if they were clocks. They're not really. So one that we like to use a lot is reactions where you go through a long-lived resonance so that you have an initial state, a final state, and a period of time in between. A plus B goes to C plus D through a resonance, or C plus D goes to A plus B. Those have reversed reaction directions, but they both run in the same clock direction. Likewise, there's a conventions on whether you call e to the minus IET positive energy or negative energy. So you have to sort through all those. The core convention, however, that defines everything, that I think is the immutable one, is that kinetic energy is positive. That tells you that in these reactions, A and B and C plus D both carry positive energies. And that's going to be the convention that determines things. Finally, I have to comment on the fact that time reversal symmetry is an anti-unitary symmetry. Anti-unitary means that you take the complex conjugate when you do a symmetry transformation. And you can find various derivations of this. This is the simplest argument I know of. X's position is even under time reversal. Momentum should be odd, but momentum is I d by dx. So your d by dx it doesn't change, so the I has to change. Anyhow, I'm going to assume that everybody knows this, that we're going to use the fact that time reversal symmetry uses complex conjugation, and T violation is due to complex phases in a Lagrangian. All right, so here's now the meat of this topic. I'm going to try to tell you that there is an arrow of time that comes in quantum field theory, which defines the past light cone and the future light cone, and those reactions then define the arrow of time. That's where I'm trying to do. Now, if you look up in a quantum field theory book, the causality in the index, and you turn to the page, you're always going to find the following. You're going to find that causality requires that operators commute at space-like separation. It dates back to this classic paper by Gelman, Goldberger, and Thiering. There's space-like separation is then listed there. And this is the tough thing you have to enforce, and you can do it. Of course, quantum field theory does it. But there is more to that. There is a directionality. And you can see the directionality by looking at the Feynman propagators. The the propagators actually, as you all know, when you draw the Feynman diagrams, those aren't space-time diagrams. They're just connections. But you can decompose them into time-ordered components by doing the contour integral. The fact that you put this I epsilon down there tells you that the poles are in various locations. You then close the contours depending whether t is positive or negative, and you get the propagators with a forward or backward direction. The result with the standard conventions is that positive energies propagate forward in time. Negative energies propagate backwards. That is what is needed to do causality. But if you're then taking along the resonance, you take A and B in, you go through a resonance, the initial state carries positive energy, it propagates forward in time. So you can start here seeing the arrow of causality. Positive energy propagates in one direction only. So when you do reactions of positive energy particles, standard conventions, it's forward in time. This I epsilon has broken that classical symmetry and defined the past light cone and the future light cone. You can, this is the arrow of causality. When you produce an initial state going into a resonance, that resonance decays later being later in time. So while you can test time reversal by running reactions backwards, the experiments actually run the reactions forward in time. So causality goes one direction. And just another side comment is that in resonances, you basically take I epsilon, replace it by I gamma. Okay, let me not do much about that. But now here's the real question now. So we've seen that there is a directionality. It's that in quantum field theory. But is this something that's fundamental? Is it did we have to do that? Where does it come from? Can we use plus I epsilon here, and behind the moon we use minus I epsilon, and then have things running in different directions? Or if the relativists are right, is the residual of the Big Bang, where does it come from? Okay, is this part of the laws of physics or just a choice? Like our choice of using retarded propagators in ENF, retarded Green's functions. So the bigger question has to do with this. It comes with a factor of I. Why can't we just change the factor of I? My colleague Barry Holstein used to be sloppy with signs. And if he made a sign mistake in front of a factor of I, he'd always say, physics doesn't care about the sign of I, and change it. And in some ways, that's right. In particular, classical physics doesn't care. There's no factors of I in classical fundamental laws. We've learned to use complex numbers in doing analysis, but it's just a tool. All the objects that you're dealing with are real. The electric fields are real. There's no factor of I in classical physics, really. Quantum physics is different. It has some real hard factors of I. When you do commutators, you have IH bar. You do path integrals, you have e to the IS. So the question and the direction we're heading now is trying to relate the I epsilon to these hard factors of I in quantum physics. And that's let's do that. What if I did a path integral with e to the IS, e to the minus IS, instead of e to the plus IS? Okay, we normally do path integral sum over all fields with e to the IS as the weighting factor. If I change that sign, what happens? Well, there's a couple of ways to do it. I'm going to do it first staying in Minkowski space. Staying in Minkowski space, I'm going to want to make that path integral better defined by adding a real number that suppresses high fluctuations. You then complete the square and you get out your propagators for your generating functional, and from these you get your Feynman rules. In this case, if I used e to the minus is, I get two minus sign differences. I get one in the numerator, one in the denominator. But in particular, the one in the denominator, I go from plus I epsilon to minus I epsilon. So I've connected the I epsilons in the propagators to the i's in the path integral. Another way to get this is by starting from a Euclidean action, which is positive, definite, and well-defined, and then getting Minkowski by Wick rotating. But if you want to get e to the is versus e to the minus is, you actually rotate different ways. And you put your poles in different places. So instead of the usual poles, you put them off in some other places so that you can do your Wick rotations correctly. You get the same result that I got just above. You get these, the I epsilon changed. It's not surprising because you're basically changing a factor of I. So you change your factors of I, your residual factors of I. You start off with a real path integral and you end up with one factors of I changed. But then if you look at this guy, what do I have? I have a time reverse propagator. Positive energy now propagates backwards in time, and instead of forwards in time. And you use that to generate amplitudes, you get time reversed processes. This has the opposite arrow of causality. So instead of going to positive times, it goes to negative times. And this makes total sense. Time reversal is anti-unitary, if you remember. The Lagrangian was, in this case, was simple, was invariant. But the path integral had an e to the is. And under time reversal, anti-unitary goes e to the minus is. So the path integral changes from z plus to z minus under time reversal. And the other quantization conditions also change. I'm not going to do canonical quantization here. Gabriel and I in our paper have that. Sorry. So what we found is that the path integral with e to the minus is looks like the same theory, but time reversed. So the Lagrangian itself is t invariant. The path integral is t covariant. It just flips sign. It basically is the same physics, but a different clock direction. So if you lived in a culture that counted down for time, you would use e to the minus is. The usual. So we've connected the directionality to the choice of e to the is. So far we've seen there's an arrow of causality determined by I epsilons. Classical physics is bidirectional, but quantum physics is unidirectional. It has a definite path light cone. And the I epsilon is determined by quantization by using I epsilon, is in the path integral. So this is where the factors of I come in. Since we're, okay, this then determines the arrow of thermodynamics. Reactions follow the causal directions. Entropy increases in the same direction of causality. So arrow of causality determines arrow of thermodynamics in a connection that is not evident in the literature. Since we're particle physics people here, I'd like to do a few slides on the test of time reversal symmetry, because this actually helps explain some of the funny things that you do when you're doing symmetry tests of time reversal. Now, time reversal violation can happen when there are phases in the Lagrangian that can't be removed. Those phases are not the source of the arrow of time, but they're small phases that violate time reversal symmetry. But there are things that are not often said when we're talking about these. One is that we don't actually do time reversal because you can't reverse the time. You compare two related reactions, run forward in time. And there are consequences of that. And the other is that the T violation is small and measurements are real, so you need to interfere with other things. So you also always should check to see what you're interfering with. And it tends to be things connected to I epsilons. But that's a little smaller. But here's an interesting case. The spin asymmetry and beta decay. The spins and momentum are odd under T. The asymmetry sounds like it should be odd under T, but it's not. You can measure a spin asymmetry in a T conserving world. And why is that? It looks like it's odd under T. It can be traced back to the fact that we don't actually reverse time. We run things forward in time, and final state interactions generate phases. Those phases come from I epsilons, and we're not reversing those. If we were able to really reverse time, it would be a test, but we're not. We run things forward in time, and the I epsilon gives you the imaginary phases that are needed to generate them. This I learned from Emanuel Durman back many years ago. Another example that's often cited as evidence of T violation is K on oscillations, where you compare K0 to K bar to the reverse reaction. Here you're reversing the reactions, but you're running them both forward in time. Both of them are measured at later times. This is like this AB to CD type thing. Here there's also an interference, so the imaginary part of M12 is time reversal violation or CP violation, and delta gamma is from the I epsilons. So you see the interference there. But Wolfenstein pointed out that this is actually not time reversal violation because it can be faked if you have a T conserving CP violating interaction. It's only T violation if you have a Lagrangian where CPT is automatically satisfied. It's really CP violating, but it does probe the T violating phases in the Lagrangian because Lagrangians conserve CPT. Anyway, so this is also a funny one in that it's actually not run backwards in time. Dipole moments, electric dipole moments actually have the same thing, but there are no final state phases, and the beta against no final state phases, so you actually get a clear signal. But anyway, classical physics is, my takeaway here is bidirectional. Quantum physics is unidirectional. The direction is determined by the quantization, and that's our standard conventions are the ones that determine the time direction. So in some sense, this is an important message for the arrow of time. It's not as surprising a result in quantum physics as it is in classical physics. Okay. I'm going to move on. I guess I could take questions there, but it's your choice. I'm going to now move on to Ostrogradsky, which you'll see is also somewhat related. Okay, so the story of Ostrogradsky is a mathematician from the past, from the 1800s, basically proves that in theories with higher time derivatives, you get a Hamiltonian out that's not positive definite, even at low energies. And so this is an instability that's used to rule out higher derivative theories. However, we'll see that that his choice of the Hamiltonian is not necessarily the choice that quantum physics makes. I'll review his after I do the example, but my goal here is first to do a simple example that I think we can walk you through and you will believe every step of the way, and then we'll see Ostrogradsky. So the very simple model is the following: is you take a light field, which is like the photon, except it's a scalar. So this is a scalar model of QED, or general relativity. I'm going to pretend that m is 0, but we don't have to. And so it's a very light field coupled up to something that's like an electron. It's a scalar version of electron, charged or a complex scalar field. And they're coupled up linearly so that you get typical diagrams that do it, photon exchange. If m was 0, it has a classical wave equation as the solution and the long wavelength limit. This has a well understood classical limit. And now I'm going to make this thing very dangerous. I'm going to take the same theory that started out, that guy's going to be almost nothing, but add higher derivatives. And I'd like you to think about this mass, big M, being like the Planck mass, where we can't see that this becomes a very, very tiny correction, because that mass is so big, we're not probing it yet. Ostrogradsky says that this theory is unstable now, that it has no classical limit because the Hamiltonian is not positive definite even at low energies. Now, we know we're going to have to give up something. There's something going to have to be given up because this is a problem. But is Ostrogradsky right? So let's analyze it. I'm going to also use path integrals to define this. The path integral is just done by integrating over the field phi. I'm going to use an auxiliary field to get rid of this term. And you do that just by putting in this new field eta, which when you integrate it out, gives you the same effect. So I've not done anything new here. I've just used this auxiliary field to replace that by a new field. And then I do a field redefinition, which is an allowed one. I change from phi to a and eta. And very interestingly, I mean, this was chosen this way, of course, the Lagrangian totally separates. I get the original simple model with a photon-like field coupled up to the matter field. And I have a field, this eta field now, extra degrees of freedom, coupled with a big mass, coupled up to the same fields, but now it's a very massive field. But the interesting thing is, or the important thing, is that there's a minus sign here. That's scary. But if you go back to the path integral, it's not that scary, because I use e to the is, and so the first term has e to the plus is, and the second term has e to the minus is, which we've already seen. So the path integral for eta is just a complex conjugate of a normal path integral. It actually, despite having that minus sign, it's not that scary. It can be done exactly. And you get the propagator. So we had before with the minus I epsilons there. You take the low energy limit, it just becomes a contact interaction, just like the exchange. So this is exchange of a very heavy particle, a Planck mass particle. it gives a tiny little shift in the self-coupling of the chi fields. But that can be taken to be arbitrarily small by making the mass so big. So integrating out this heavy field, this extra field, gives me back the original theory with just a tiny little change. So the low energy limit is just a normal theory. Ostrogradsky was not right here. It has a normal classical limit. At high energies, it's a little different. At high energies, the most important thing is that this heavy state decays. There's a self energy picks up an imaginary part. It decays into light states, and you can analyze that. I'm going to go quickly through that for time reasons, but basically you shifted minus I epsilon goes to minus I gamma in this change. It's like a resonance again. The energy flows now are funny. There are poles all over the place because of the two propagators. The light poles have the usual behavior, and you're not surprised now, since it's made a big difference on it, is that the energy flow in the heavy poles goes the opposite direction. But they still decay. They don't exponentially blow up. They're still decaying. Okay, and they're also still positive energy and I measure energy by producing them. I take two of these initial states, I scatter them, I produce the resonance, I get the two states out. The initial and final states are positive energy. The resonance is positive energy. So it's a positive energy resonance, but from our previous work on the arrow of causality, we know it's propagating backwards in time. So it's weird, but it's positive energy. So this at this stage seems like it's stable, positive energy. So some of the myths about higher derivative theories don't seem to be evident here. What would Ostrogradsky say? Well, Ostrogradsky notices that these higher derivative theories have to have extra coordinates and momentum because the extra degrees of freedom, which we also found. And he chooses one of the canonical coordinates to be phi and the other to be phi dot. Okay. Then there are canonical momentum associated with those. You form the Hamiltonian in the usual way. There's a slight change in that you have to eliminate by double dot. But in the end, it's once you've made those choices of coordinates, it's a straightforward exercise to give you your Hamiltonian. And the Hamiltonian here now, so in a Hamiltonian treatment, you treat your coordinates and momentum as independent variables. If you look at this, the danger is sitting up front. The pi 1 only occurs in the first line there. Nothing in the rest of the construction depends on pi 1. Pi 1 can have either sign. Phi 2 can have either sign. So this treated as a Hamiltonian indicates that the Hamiltonian is not positive definite. There's nothing to bound it from below, so it's unstable. Okay, so that's Ostrogradsky's statement. It looks a little funny from the perspective of quantum field theory because we didn't see any. Well, we had one of the choices was phi was a coordinate, but the phi dot being the other coordinate was not there. Why did he do that? Well, his goal was to reproduce Hamilton's equations. And if you go back and check, you find that the Hamilton's equations are in fact satisfied, and the Euler-Lagrange equation is a Hamilton's equation, equivalent to a Hamilton's equation. But there's no reason, we don't need this. Quantum field theory doesn't require that the usual Hamilton's equations be reproduced. It requires to identify quanta, and we've done that. So the Ostrogradsky construction is not the classical limit of quantum field theory in this case. It is funny, it is a funny theory, because we have seen that there's two states. There's the A state and the eta state, or here you can even see it in the propagator. You do take something with a quadratic and quartic terms in it, and you partial fraction it, you get the same result. You get a usual massless propagator and a heavy one with the wrong sign. And we notice that there's a minus I epsilon here, plus I epsilon here, because we did the construction in more detail. And those are dueling arrows of causality. And so we have some causality violation. The stable states win because they're the only ones that propagate over long distances. But there is over short scales some causality violation. And I'm actually going to skip a bunch of things here because of time. I can't resist the cutesy story here. Gabriel and I call these things Merlin modes because the wizard in the King Arthur tales ages backwards in time. The quote here says, lives from backwards to in front. And that's the distinction here compared to usual ghosts. So these are ghosts, of course. Everyone, I'm sure, recognize that those are ghosts. But Fidea pop-up ghosts have plus I epsilon in the denominator. These guys have minus I epsilon or minus I gamma. So the distinction of this forward or backwards propagation of ghosts is in the denominator. There is some phenomenology, but again, for time reasons, I'm just going to skip it. I'm going to say, for gravity, where we're going to use this, it's all the Planck scale, so we're not going to worry about it. So last few minutes I want to spend on coming back and talking a little bit about quadratic gravity. So we obviously are going to have some issue here. And we've started to see that issue because quadratic gravity is one of these theories with 2 derivatives and 4 derivatives. The brief summary is that the spin 2 propagator is the dangerous one here. It has a Merlin mode, so it's a ghost with the opposite sign of I epsilon or I gamma. Propagates, it's a positive energy resonance, positive energy. It's one of these theories that's in the category that I described the simple example there. It seems to avoid Ostrogradsky at low energies. It definitely has some causal issues because of that backwards propagation. Surprisingly, unitarity works, and Gabriel is going to talk about this tomorrow in the sessions on other theoretical developments. This is, as I say, it's surprising, but it's, if you understand the unitarity of unstable particles, you actually are not as surprised, because Veltman showed that when you do unitarity sums, you only include the stable states. You don't include unstable states. And here, this resonance is an unstable state, so it doesn't appear in the unitarity sum. Only the light particles, the stable particles, appear in the unitarity sum. And they, in this construction, all come with plus I epsilon. So it takes some work. I mean, that's a non-trivial statement, but you should see Gabriel's talk and also see our papers on it. It's not clear totally that this is going to be a perfect quantum field theory. I've only argued for stability at low energies. The stability at high energies may fail. It's less clear. Certainly more work is needed, and we have a fun project underway trying to understand the quantum field theory of this in more detail. Others are also working on that. But let me then summarize the whole presentation. Most of the topics, the main topics that I talked about were funny in the sense that the classical statements that you would think you could describe classical physics with were modified by quantum physics. The causality, the arrow of causality was not visible at all in a classical Lagrangian, but it's there in a quantum Lagrangian, and it's traced to the way we quantize the theory. But nevertheless, it has a manifestation in the classical world. Likewise, the instability that Ostrogradsky would have predicted doesn't seem to be there in quantum field theories, at least some of them, because they form your Hamiltonians and they form the low energy world by a different construction than the one that he proposed. These are interesting and a lot of fun to work on, because you start questioning all the things that you've ever learned about quantum field theory, but that makes it fun. And it's even more fun if this is relevant for the great unsolved problem of our time, which is the nature of quantum gravity. So let me end there and I'll take questions.
Okay, John, thanks for the great talk. And I think we can take questions. If anyone wants to question, please go ahead.
Let me see if I can get, so I should stop the sharing of the screen so I can see people if they'd like to ask questions.
Yes. So I think anyone who wants to ask questions can just unmute yourself and go ahead or write in the chat and I'll ask them.
I can ask a question if you want.
Yeah, of course.
Sure. John, it was very nice talk. I liked it very much. Thank you. And now I understood something. But I think there is a big difference between this phi cube theory, which you presented as an example, and gravity. And the reason is that in phi cube theory, you can separate the negative energy model and integrate it out in quantum theory. And this can be done because the theory is polynomial, but gravity is non-polynomial, so you cannot isolate it. Do you have some hint how to deal with this subject?
Yeah, certainly at the quadratic level. So if you're just doing the quantization, you can do the same thing. You could define a new field. What it means is that the interaction terms that appear at higher orders will be coupled. And if I'd made a slightly more complicated scalar theory, I could have mimicked that also. I deliberately didn't do that because then I totally separated out the modes. But if you did it for a theory that had complicated quartic interactions, for example, quartic interactions would be ones that didn't totally separate. You would find that there'd be then new interactions between the heavy Merlin ghost, the massless particle, and the matter fields. So you just have more complicated interactions, but your initial ground states would be the same, have the same pattern. And now, of course, this means that the analysis of gravity is going to be more difficult. But we've at least tried to get past one of the conceptual problems. And now we have a quantum field theory of gravity that's a difficult quantum field theory that we have to analyze. Or I'll let you analyze it. Because it's, okay, you know, so it replaces one of the conceptual problems with a difficult set of quantum field theories.
Understood. So you basically, you say that canonical quantization anyway is performed for free theory. So
right,
at this level, there is no big difference. Yeah.
Right.
No, I agree with that. But the question is whether it has some relation to the final goal, let's say.
Yeah. Yeah. I mean, that's of course our research projects, and some of yours too.
Anyway, as I said, it's very interesting by itself. So I agree.
Right. You know, so far I haven't seen anything discouraging. You know, so to me, this is it's a question that I'm just personally curious about. Is this renormalizable quantum field theory, quadratic gravity, is that a viable option or not? And if it's not, I take that and I'll move on to something else. But the more I look at it, the more it looks like it seems viable. So I might as well keep exploring.
We have some results on stability in this theory, classical stability.
Yes, I know.
And
actually,
it shows that it depends a lot on the initial conditions.
Yes.
So in some situations, it's like what Simon described it in 1990. Very close. But for that, you need to avoid Planck density of gravitons. If we have some physical principle which forbids Planck density of gravitons, it will be just perfect, I would say.
Yeah, no, that's right. So I also, you probably noticed that I think you've seen one of my other talks where I do have a slide that references some of your work on that. I did take it out here because I was not talking about gravity as much. But yes, I think the stability at high energies, high curvatures is one of the major open questions in such a theory. And yes, we know you've done some nice work on that.
Okay, thank you very much.
Yeah.
Just let me add a comment that if you're interested in calculating scattering amplitude at a Minkowski background level, you can also use the quadratic gravity, and you can use the double copy procedure. And so far, we didn't find any problem in doing that. So, of course, the fact that the theory is unitary helps a lot. So,
there was Gabriel. There was recently a meeting about these issues in Tokyo, online, of course. And some people reported that when they calculated amplitudes of scattering in R-square gravity, and even in the non-local version of R-square gravity with non-local form factor between Y square and R-square curvatures, the result is identical to the amplitudes in the Einstein theory.
Well, depends on the content of the scattering amplitude.
Or maybe this you know better than me, but
Yeah.
I think I even know why this happens actually.
Yes,
So
if you scatter only gravitons, yes, that's the same. That's the same.
no, they scatter everything. No. Maybe
No,
you're right.
I think
Maybe
their
you're right.
results were actually just scattering gravitons.
Yes.
Yeah,
yes,
you're right.
it's
You're right.
scattering gravitons.
And that's the equations of motion at work where
Yeah.
R is equal to 0 for
Exactly.
gravitons.
Exactly.
Yes, that's the same. Yes, but if you separate things as we do, yeah, you separate in a graviton in a massive ghost, then you have an extra degree of freedom to scatter. Then you have extra.
No, then there cannot be equivalence. I agree. Okay.
Yeah, that's different. So any further questions? So I don't see any raised hand. So perhaps we can close the session now and thank John for the great talk. Of course, I'm very suspicious to say that, but it was a very great talk. And now we move on to the next session. I think we have parallel sessions right now. And thanks everyone. And I hope you continue to have a good time. Thanks, John, again. Let's thank John.
Great. Thank you all.